The history of engines in warships only spans a couple of centuries, a far shorter time than ships have been in existence, but enough time for radical change in the field of naval propulsion. We've already covered boilers, the things that generate the steam, and later on we'll cover propellers, the main form of actually moving the ship around for most powered warships. But today, we're going to take a brief look at what sits between the boiler and the screw or paddle wheel in order to ensure that the ship can move. Now, notably, we are only going to be looking at the main developments of the marine engine, rather than looking at every single possible subvariant and dead-end design that ever was come up with. So, with that in mind, steam engines had been around for about a century, just over, by the 1820s. Although most of that time they'd only really existed as massive low-pressure fixed installations which could pump water out of mines and drive factories, but little else. But the dawn of the 19th century had seen several advances in raising the pressure that could be used in steam engines, and this in turn gave a much larger power output for a given size of engine, and this began to make the idea of an engine that was small and powerful enough to be used on a mobile platform instead of a fixed installation somewhat more viable. Due in part to the fact that, ships are simply much, much larger, ships would be the first application of this technology, with various experimental steamships beginning to be devised in the late 1700s. But the first use of steam power in a military application was probably the paddle-powered floating battery Demologus, later Fulton, which was developed for but not completed during the War of 1812 on behalf of the US Navy. However, her nature meant that she was effectively confined to harbour. The use of steam power fully at sea would have to wait until the deployment of ships like HMS Comet, a paddle-powered tug launched in 1822. Along with other small ships like the Monkey, which displaced about 210 tons, and which used Boulton and Watt steam engines that had around about 80 nominal horsepower. Some of these engines had 2 cylinders, and could work at maybe 1 revolution every couple of seconds. The Monkey was followed in service by the Active, which also had 80 nominal horsepower, and then the Lightning in 1823, which had 100 nominal horsepower. These early steam vessels were mainly used for towing and general harbour and coastal purposes. They couldn't really be called warships. All of these vessels were propelled by paddle wheels. The limitations in terms of perceived vulnerability and the amount of space along the side that the paddles took up would mean that a full-on warship intended for the line of battle running on steam would have to wait for a little bit. But these early ships used some of the earliest form of steam engine equipped on a warship, the side lever engine. This was a step up from the simple beam engine that was the ancestor of all other types. The side lever engine was a fairly tall mechanism. As with all steam engines, pressure built in the cylinder, which then forced the cylinder head to rise, and once the cylinder head got to the top of the cylinder, the steam pressure was released, and in the case of the side lever engine, the resulting weight and vacuum drew the cylinder head back down again, where it would repeat the cycle. In the side lever engine, the head was connected to a rod that lifted one end of a large iron lever, or sometimes 2 for balance purposes. This would then cause the other end of the lever to rise or fall in opposition, and that, in turn, was connected via more metalwork to a crankshaft that generated the rotational motion. Compared to a beam engine, where the lever was mounted quite high up, on a side lever engine, the heavy levers were mounted much, much lower down, which gave the entire engine a quite low centre of gravity and made the entire thing a little bit shorter in the vertical element. This was important on a warship for both stability and tactical considerations. Even if it was mounted quite low in a ship, a tall engine could end up with a substantial portion of itself above the waterline, and that in turn rendered it very vulnerable to being disabled by gunnery, usually accompanied by some kind of disastrous steam explosion to go along with it. The side lever engine was still somewhat tall due to the size of the cylinder that was needed to get a useful working pressure, and ships up to and including the American Civil War period would still sometimes end up losing power to hull shots crippling the upper parts of their engines. But the risk was somewhat smaller with a side lever engine than it was with some other earlier engine types. The two main issues with the side lever engine were firstly that it could only realistically power paddle wheels. That wasn't so much of an issue in the 1820s, but it was something that would rule against its continued use as time went on. The other issue was that the normal twin levers and all the various connecting rods made it overall a very heavy engine for its power output. Whilst it was running at a somewhat higher pressure than older engines, that simply meant that PSI values could be read as whole numbers above atmospheric pressure, and they actually did some useful work beyond creating a vacuum, which in older steam engines, especially mine pumps, had actually ended up being the thing that did most of the heavy lifting. Between the early 1820s and 1840, 70 additional steam vessels would be added to the Royal Navy alone, let alone all the other navies that were quite rapidly adding steam warships and ancillary auxiliary vessels to their forces. The majority were fitted with the side lever engine, and this tended to work at a steam pressure of about 4 pounds per square inch above regular atmospheric pressure. The Rhadamanthus was typical of ships of this period, although it should be noted that, like many such ships of this time, the nominal horsepower was 220, but the engines could be worked up to around 400 indicated horsepower, almost double the nominal. The load on the safety valves was once again around 4 psi, and the number of revolutions when it was going full on was just under 18 rpm. This required machinery of about 275 tons, which was quite a considerable mass for warships of this period, especially small ones like Rhadamanthus. After the introduction of the side lever engine, a number of variants on both older beam and the side lever engine itself were developed, often with quite significant regional uptake local to the developer who'd invented it, and occasionally they would see significant uptake across the world after a short period, but most of these variants were largely civilian developments and would not feature in warship construction except in extreme circumstances, such as the American Civil War, where merchant vessels were taken into military service and converted into warships, despite the fact that their engine design may not be necessarily optimal for a gun engagement. The main reason for the lack of use in ships actually designed for combat was that, similar to the beam engine, most of these variants had significant weight and carried a lot of that weight at height. On a merchant ship, that was less of an issue, thanks to the large amounts of cargo they carried tending to have quite the ballasting effect that would mitigate any stability issues, whereas on warships they were already carrying quite substantial weight much higher than on a merchant ship due to having to carry guns and the associated gun crews. And when such converted ships ended up in combat, once again these tall engines could often prove to be something of a weakness. But the increasing prevalence of the screw propeller demanded a new kind of engine. The conversion of older ships to block ships, these usually being Napoleonic-era ships of the line, typically a third rate, that had been converted to carry a steam engine, and then being used either as a guard ship for a harbour or as some kind of wind-independent coastal defence force, as well as much more ambitious plans to convert larger vessels to carry auxiliary steam power plants, plus of course the construction of newly built smaller vessels, saw a wide range of systems tried. Even though the steam locomotive had actually been a slightly later development than the steam-powered warship, in some cases what amounted to steam locomotives that had had their wheels taken off were used for lower power application and auxiliary plants. This wasn't ideal for a number of reasons, but these power plants could at least drive a screw propeller and were somewhat readily available. Two particular ships stand out in this period of development, which ran from roughly 1830 to 1850. HMS Rattler, the British screw sloop that famously engaged in a tug-of-war with the paddle-powered HMS Alecto, and the French line of battle ship Napoleon, which was the first purpose-built steam-powered capital ship to enter service. The former vessel, Rattler, used an odd engine type that didn't really catch on in warship circles. The Siamese or twin-cylinder engine worked on the same kind of pivot and lever system principle as earlier side lever engines, but instead of a single larger cylinder, it used two shorter cylinders to provide the relevant motive force. This allowed the engine to be somewhat shorter in the vertical element, and the two cylinders meant that only a single arm was mounted in between the two cylinders instead of the two arms more commonly found on either side of a single cylinder in a side lever engine. It was compact and slightly lighter than the older engine, but it nonetheless reflected the growing divergence between civilian and military engines, as its primary attraction was the fact it didn't interfere with the lower parts of the gun deck as opposed to any particular fuel efficiency. But the multiple stages of leverage between engine cylinder and crankshaft in any of these types were somewhat inefficient in terms of transmitting power to the screws, and all of that metal was quite heavy. A change was needed, and so engine technology began to advance to direct drive type of engines. In the paddle-wheeled ships, which were still in use as tugs, sloops, and other vessels that were not considered likely to see much combat and definitely not going to stand in the line of battle, one of the first direct drive engines was the so-called Oscillating Engine, which was used almost exclusively to drive paddle-powered warships. Simply put, the direct drive system allowed the cylinders to impart power directly to the crankshaft, making the entire system significantly lighter and more efficient than older types, since the beams and most of the rods could be done away with, and there were fewer stages of energy transfer in the system. However, they required the cylinders themselves to be able to move to account for the crankshaft rotation, something which had previously been the concern of the intermediate beams. It also concentrated quite a few separate movement aspects into a number of fewer components, which made the savings described earlier, but also meant that those individual fixed components were far more complex and thus far more difficult to maintain. The requirement for the moving cylinders was a particular sticking point with this kind of engine, as it also meant that the feed for the steam line had to be fairly flexible, and, well, if anything went wrong, you had a cylinder full of hot steam that was moving back and forth, which was not that easy to get anywhere near. The other issue was paddle wheels just needed to rotate somewhat slower than screws, and engines had therefore been designed for this level of rotation. This was where Napoleon comes in. Although she wasn't the first ship to introduce the direct drive engine, her use of one to drive a screw on a large warship posed the problem of using an engine that had a relatively low set of revolutions per minute with a propeller that needed to go somewhat faster than that in order to get the ship moving at any appreciable speed. This would be solved by introducing, at least temporarily, another innovation: gearing. In this case, stepping up the revolutions per minute, albeit that this required an exceptionally powerful engine for the time, since, of course, each revolution of the engine had to drive several revolutions of the screw, which divided the overall power, hence the need for a high starting energy so that enough was left per revolution to turn the propeller against the resistance of the water in most sea conditions. Needless to say, this also required a lot of maintenance and contributed somewhat to a reputation of the ship for its steam plant's unreliability. Steam was at this point also still very much an auxiliary. The massively inefficient use of the power of the boilers, and their, by later standards at least, very low pressures, meant that a ship would burn through any reasonable coal stock long before it got even half as far as a sail-powered vessel could do, since they relied mainly on how much food and water they carried, and hence all but the most coastal of craft would still carry a full set of sails, and would continue to do so for quite some time. In order to travel any substantial distance by steam, ships would need to be much, much larger, exploiting the square cube law to disproportionately increase their coal storage capacity, which would lead, in the civilian world at least, to the building of the SS Great Eastern. But since she cost more than twice the amount of any two of the largest steam-powered ships of the line that you can find put together, and that despite there being basically no cost involved in arming the Great Eastern, since, it didn't really carry all that much of an armament, that kind of size of ship was not a viable path for warship design, no matter how generous a budget you had. Instead, the trunk engine would be developed. One of the ways to improve reliability was to have a longer power stroke, as this distributed the force exerted on moving components over a larger distance, and thus kept the strain on the individual components down. But this was counter to the need of warships to keep the engine levels below the waterline. And so the solution, it seems simple on paper but was relatively difficult to pull off in practice, was to lay the whole thing on its side. And now you could, within the confines of the ship's dimensions, have as long a power stroke as you liked. Stop giggling there in the back. Without any issues from incoming fire overhead. As the cylinder width was now, technically speaking, the cylinder height, the cylinder itself could be made somewhat larger. This allowed the connecting rod on the cylinder head to oscillate within the cylinder run itself. And that meant that the cylinder could go back to being fixed, rather than moving back and forth on the oscillating direct drive engine, which further improved reliability. Able to run up to the kinds of speeds that would be needed to run a screw propeller without gearing, they powered the last generation of wooden screw ships and would also find a home in the first ironclads. HMS Warrior, another pivotal ship, was equipped with this kind of engine. At first, the trunk engine was a fairly substantial bit of kit, in part due to the drive for reliability and low maintenance requirements, which are key features of military engines where at all possible. However, the pressures of war often lead to innovation, and working from a fairly solid base of engine technology in the 1850s, not only would the trunk engine enter widespread service, but as a result of the Crimean War in particular, it also proved possible to make it considerably smaller, increase the working pressure, and up the speed of rotation. This was largely thanks to a Royal Navy order for dozens of steam-powered gunboats, whose small size needed a smaller engine, and for which this new engine was mass-produced, which also ended up lowering the per-unit cost, and led to a raft of spare parts once the gunboats themselves were put into sheds and mostly forgotten about as the Crimean War came to a close. And that in turn meant that the trunk engine, in both its large and smaller configurations, became very common in both the military and civilian worlds for several decades, until the advance of newer technologies rendered them unable to compete. An even smaller variant that used two cylinders to generate the combined power output of a single larger one was developed for use on US monitors during the American Civil War. This was done purely to reduce the overall height to the absolute minimum possible, as the engines needed to fit in the extremely low draft and low freeboard hulls of American Civil War era monitors. However, the additional complexity of the type for the same power output meant that they didn't really see that much use outside of this rather specific niche. Following the success of the trunk engine, a number of other horizontally mounted engines were developed by companies familiar with the older style of engine building. But these tended to be effectively an older engine design, usually one of the tall ones, except now only sideways. This had certain advantages in terms of parts commonality and reliability, but came at the expense of efficiency. They also tended to have considerable additional weight and a lower power output due to reintroducing more of the intervening rods and levers, as seen in the older naval engines, and this meant that these engines would usually only be installed on warships where steam power was seen as a necessary but highly auxiliary form of propulsion, and thus the cost of the machinery was far more important than specific efficiency or range. So many composite gunboats, composite sloops, corvettes, and the like would be fitted with these kinds of cheaper but less efficient power plants. During this period of development in full-on line warships, however, another major advance was made in engine technology. As mentioned at the start, early steam engines used steam to power one stroke of the engine, and the vacuum that was left in its absence, along with usually a mixture of gravity and momentum, kept it going through the other stroke. But this was also another area of inefficiency, and commensurate with the growth of the steam warship came the invention of the double-acting steam engine, in which steam was fed into both ends of the cylinder, alternately, depending on where the cylinder head was, ensuring power on both the upstroke and the downstroke, and thus boosting the output of the engine overall. As time went on, ships also got considerably larger, and that meant that there were larger engineering spaces, and thus more underwater volume. And that in turn allowed engines to rotate back to being mostly, or in some cases entirely, vertical, without compromising the ship's durability in combat, since they'd still be below the waterline. Also, during the period from the introduction of the trunk engine to the re-emergence of the vertical type, steam pressures had been climbing steadily from around 30 psi above atmosphere to about 60 psi. Which meant that for most ships the power available to their engines had approximately doubled. As the general principles behind cylinder-equipped steam engines had now been pretty settled, the latter part of the 19th century would see the efficiency of the use of the power provided by the boilers increase. This followed two lines of connected development enabled by boilers themselves getting progressively more and more capable, as potential available steam pressure would roughly double again to around 120 psi by the 1880s, and by the turn of the century some cruisers would be running on double or more of that again, between 240 and 300 psi. Firstly, the addition of multiple cylinders on full power engines, as opposed to multiple cylinders used purely for reasons of space or stability, such as in the US monitors or on oscillating engines, came into effect. The second was the use of multiple expansion stages. This was made possible by the aforementioned increase in energy present in the steam. Although experiments with various ideas had been ongoing almost as long as warships had carried steam engines, the idea was essentially that when the steam left the cylinder at the end of the power stroke, it would normally go back through a condenser and thus back to the boilers. But it still had a certain amount of energy that could be utilised if the energy remaining was high enough to do some kind of useful work. And thus, if instead of going straight to the condenser, this steam was fed into another lower pressure cylinder, which could then provide some additional force to the prop shaft, the steam, now with a lot more energy removed from it, would then be able to return to the condenser. Typically, the first higher pressure cylinder would be smaller than the subsequent lower pressure cylinder, which accounted for the final expansion of the steam, and this allowed a couple of different options. By using steam at the same starting energy state as before, fresh from the boiler, because you could extract more of that energy, you could boost efficiency. In fact, you could even lower the energy in the original steam feed, and thus burn less fuel to a degree, since you'd end up with about as much energy going to the screw as with a single expansion engine, because you're extracting more of that smaller amount of energy. Alternatively, you could increase the amount of energy in the steam coming out of your boiler, since the significant excess that you'd get out of the first stage now wouldn't be wasted, and thus you could go faster because you were getting significantly more energy into your propeller shaft. Keeping the energy level of input steam about the same as before, which was effectively the first option we mentioned, was seen as something of a balance between the two, with either extreme possible, i.e. much higher speed, or much better fuel efficiency, depending on what outcome you preferred for the ship that the engine was being built for. For example, a torpedo boat, for which speed was paramount and range was almost a non-issue, would want the absolute maximum power you could get out of it, whereas perhaps a corvette or some kind of second or third class cruiser that had to go very long distances and didn't have to worry too much about maximum speed would be looking for a very efficient form of steam power plant. Whilst something like a cruiser or a battleship, which ideally did want to go relatively quickly, but didn't want to burn through all of its fuel stocks very, very soon, would go for a balance between the two. It should be noted that whilst a double expansion engine needed at least 2 cylinders, for obvious reasons, it was not limited to 2 cylinders, nor was it limited to pairing 2 individual cylinders. You could, of course, do that if you wanted to, but you could also, for example, feed 2 or 3 low-pressure cylinders from a single high-pressure one. And that's why in this era of engine technology, you usually see ships described with their engines being stated as X expansion, Y cylinder, or X cylinder, Y expansion, to give some idea of the overall configuration. Titanic, for example, had 4-cylinder triple expansion engines. And the reasons that you could describe the expansion as being X or Y is because it didn't just stop at 2-stage expansion. With greater power output from better boilers still increasing, it became possible to add a 3rd stage to proceedings, and thus the vertical triple expansion engine, which was the most common kind of engine in the pre-dreadnought era, was born. Whilst civilian models would later go on to develop the quadruple expansion engine, the vertical triple expansion engine represented the end of the line for this kind of engine for warships generally. However, whilst they would usually be replaced in ship design over the 1900s and early 1910s in most nations, the vertical triple expansion engine's story wasn't entirely done. During World War II, the sheer number of smaller ships being built, the lack of need for most of them to be especially fast, and the fact that cutting the blades for turbines was something of a bottleneck, would lead to the return of the vertical triple expansion engine in numerous ships such as anti-submarine warfare corvettes and even some escort carriers, as it was relatively simple, cheap, and easy to build, and thus had retained quite a widespread circulation in the civilian merchant world and their suppliers, where speeds above the mid-teens of knots were rarely required, and by that point minor improvements to the engine technology had allowed ships to hit just over 20 knots quite comfortably. There was also a secondary issue of lots of merchant sailors being taken into naval service and being familiar with the vertical triple expansion engine, which therefore needed far less retraining if you assigned them to these kinds of vessels. For most warships, though, speed was the thing that was desired, and that was something which the vertical triple expansion engine was both starting to struggle to deliver, as this climbed into the upper 20s of knots for some of the bigger cruisers, and advances in fire control also required a much smoother ride. The fundamental problem with vertical triple expansion engines, and indeed any engine of the types that had been so far used, was that a fairly large amount of metal was being hurled back and forth repeatedly, and at considerable speed. This in turn led to vibration, which could be mitigated somewhat by increased lubrication efforts as well as cushioning installations, but it couldn't be eliminated entirely, and the solutions that mitigated it somewhat led to considerable increased weight and some rather interesting effects in the engine room, as lubricant would tend to fountain all over the ship's engineers when the engines were being run at speed, such as, say, in a battle. Until the invention of forced lubrication, which was still some years away in the early 1900s, vertical triple expansion engines could also only be run at full power for a limited amount of time before risking catastrophic failure due to repeated and rapid stress. But of all of these factors, as the 1900s moved towards the 1910s, the vibration one was the most important, as this would make the use of long-distance rangefinders quite difficult, if not impossible, and that in turn would cripple a ship's ability to fight in a long-range gun battle, which was now possible thanks to the development of central director firing coupled with the new rangefinders, unless of course you went through the expense of dampening all vibration out. And thus the steam turbine, first seen in the 1890s aboard ships, began to take the place of the vertical triple expansion engine in newly built warships as the first decade of the 20th century progressed. The steam turbine worked in a very different way. Steam was still needed, but instead of driving a linear motion in a cylinder that then had to be mechanically transformed into a rotational motion, the turbine used high-pressure steam passing through a series of rotors to create rotational motion directly. Whilst the precise mechanism as to how it did this could vary, with reaction turbines, impulse turbines, and the like all being developed, the core idea was essentially the same. They could run with minimal vibration, and due to the moving parts being in simple continuous circular motion, they could in theory run at full power for as long as you had fuel to keep the boilers lit. Like vertical triple expansion cylinders, you could chain turbines together to use steam at progressively lower and lower pressures. And as even a single turbine contained multiple rotors, you could even vary the power output of the turbine itself by either releasing steam from the turbine before it completed its full run through all the rotors, or by looping steam back into the turbine to increase the overall effect on the rotors themselves. However, turbines were most efficient in terms of using the energy that was in the steam that was provided to them when they were run at near enough full power. This was great if you wanted to go really fast. It was not so great if you wanted to cruise at a somewhat more pedestrian speed, which was itself more efficient in terms of the amount of fuel burned in your boilers per hour. Turbine efficiency dropped off considerably when you ran it at these lower speeds, and unfortunately the high-speed efficiency bracket for most early turbines was several hundred revolutions per minute, which when connected to the propellers meant a lot of cavitation, and thus both damage to the propellers themselves and a loss of propulsive efficiency, as they simply spent most of the time spinning in a cloud of bubbles and turbulence of their own making if you weren't very careful. A number of different solutions were tried. On some ships, especially destroyers, they simply added more propellers to the shafts, reasoning that if you could only get 50% power output from a propeller, well, if you put 3 propellers on the same shaft, you then got 150% output, minus a little bit for the weight of the extra propellers. In other ships, a cruising turbine operating at lower pressure was added for low-speed operations, and the higher pressure, faster spinning turbines would only be spooled up for top-speed operations. In some instances, a cruising turbine might be a completely separate installation, whilst in others it could be an integrated part of an overall single turbine solution. These were only stopgap solutions, though. The true solution came about in the 1910s with the development of geared turbines. These worked in the inverse manner to the gear set fitted 60 years previously on the Napoleon. That set had uprated the engine's rotational speed to get the screw turning at a reasonable rate, whereas the new gears downrated the high speed of the turbines to a much lower speed for the screws, which would in turn return prop speeds to their most efficient regimen, and also meant that there was significantly more power behind each rotation, which in turn would allow for bigger and heavier propellers in the future, albeit it also meant multiple shafts would become more and more common, as it was now possible to exceed the reasonable physical tolerances of the propeller shaft itself by accidentally putting too much power into it. But whilst steam turbines with reduction gearing would go on to power the bulk of warships through to the end of World War II, there were 2 other systems that would compete with it: diesel and the turboelectric drive. The turboelectric drive was the closest to the existing steam engine line of development. as it actually used turbines as part of the powertrain, but instead of direct drive or reduction gearing to the propeller shafts, it used a turbine, or turbines, running constantly at their optimally efficient speed to run electrical generators instead. These generators would then provide power to electrical motors as well as to the rest of the ship, and the electrical motors would in turn rotate the propeller shafts. There were a number of advantages to this. The response to the need to change speed was considerably faster, and you could throw the system into full reverse with just as much power, if not necessarily as much speed, as you could with full ahead. If one motor or propeller was disabled by a torpedo hit, a mine strike, or some other kind of accident, power could relatively easily be rerouted to other motors within their tolerances to make up for the loss in propulsion. From a survivability perspective, you could separate out all the generator and turbine rooms and the motor rooms, since the only real connection between many of these rooms was power cables. And a burnt-out electrical motor would be far easier to repair with onboard parts than a turbine that had stripped its blades and had probably explosively disassembled itself. Another advantage was that if you lost one or more generators or one or more turbines, you didn't necessarily lose the corresponding propeller shaft, because as with a propeller shaft that had been disabled, you could also redistribute power from a single generator, or however many surviving generators and turbines you had, to all the propeller shafts, as long as, again, the amount of power that was available overall was enough to drive all the motors. However, there were a number of issues as well. The need for two whole new systems, and electrical ones at that, meant that the engine set as a whole was quite heavy compared to a direct or reduction geared turbine set. The loss of the generator, if it was on its own, or the generator rooms, if there was more than one, could cripple the entire ship, since everything was being supplied with electrical power from these areas. The electrical systems could be far more susceptible to shock damage than the relatively solid turbines, albeit, to be fair, that if a shock had reached down into your central machinery spaces, you probably had bigger issues to deal with than the fact your engines had just gone offline. But there was, of course, the other thing that in the event of combat damage that resulted in flooding, the relatively sturdily encased turbines could, and in some cases did, keep running the propellers even as the ship slipped beneath the waves, whereas the hazards of large amounts of electrical current, possibly also including damaged cabling, in a steel vessel that was rapidly filling with salt water, don't really need any further qualification. On some ships, it was also, however, possible to shorten the propeller shafts. This was an advantage, since the motors could simply be mounted further back in the ship. But on capital ships, this opportunity was limited due to the need to keep the machinery spaces inside the ship's citadel, which ideally would not extend past the aftmost turret. Efficiency was also a matter of contention. On the one hand, the turbine was able to run constantly at optimal speeds, which improved efficiency, and compared to direct drive, the props also spun very efficiently as well. However, compared to a good reduction-geared turbine set, which also broadly allowed for this difference in rotational speed between turbine and propeller, the turboelectric drive could not compete, simply because any change of energy from one state to another is not 100% efficient, and thus energy will always be lost in the transition. On a reduction-geared ship, the energy losses from the time that the heat energy of the steam was turned into rotational kinetic energy on the shaft are fairly simple and minimal. There's a small amount lost to friction and physical wear in the gearing, and then the energy's at the screw. In a turboelectric drive ship, the rotational energy is turned into electrical energy via magnetic induction in the generator. This is then transmitted, with some loss due to resistance-based heating in the cabling, to the motors, which then have to reverse the process, with the electrical energy being used to create an electromagnetic field, which will then turn the motor, which results in the rotational kinetic energy coming back again, which then goes to the screw. These additional steps drag the efficiency of energy transmission all the way back down, and so once good reduction gearing had become affordable, the turboelectric system was, for various reasons outlined above, generally dropped in warship construction in favour of the geared turbine. Diesels were another matter. These were entirely divorced from steam production. They instead were a much more recent innovation, the internal combustion engine, which did the job of boiler, turbine, and in some cases even gearing, all in one neat package. Their relatively compact size and the fact that you could simply shut them down and start them up again in fairly short order, plus the fact that diesel was much harder to set on fire or make explode as compared to petrol, meant that they would rapidly become the favoured power plant for submarines when these were operating on the surface. But when it came to competing with turbines on big surface warships, they were somewhat more difficult to maintain, and, at least when running on diesel fuel itself, about as expensive to run. Later on, it was found that a diesel engine could in fact run on similar fuel to that used in steam boilers, which reduced the overall cost of operation. Their main advantages were again the near-instant startup as opposed to the hours it could take to build steam pressure from a warmed boiler, and the fact that they simply burned less fuel, so that you could go a lot further with a diesel power plant than a steam one, assuming that you had the same size of fuel tank. But the most critical issue for most warships was power density. For a given volume of machinery, steam turbines simply gave more power than diesels of the 1900 to 1950 period. Now, you could of course have a bigger and heavier diesel plant to offset this, but this would in turn reduce the displacement available for supplies, guns, armour and the like, all of which were rather important on warships. And so, in surface warships, the diesel plant was not very often seen prior to the end of World War II, except in cases where sheer range was considered important enough that the speed drop was not seen as too massive a problem. Occasionally, this would take the form of a cruising diesel, but the calculations that went into the design of the Deutschland-class Panzerschiff, for example, took the decision that an all-diesel power plant was preferable, simply for that range advantage, reasoning that at 28 knots there wouldn't be any capital ship, at least in the enemies that the, at the time, Reichsmarine was thinking of fighting, that could actually catch them. It turned out to be possibly not the wisest of decisions in hindsight, but you can excuse them given the time when the Deutschland class was being designed. And so that completes our brief look at the various kinds of marine engine that were involved in the propulsion of warships from the inception of the powered, propelled warship up to the end of the period that the channel covers just after World War II. There would of course continue to be more advances, nuclear power, gas turbines, diesel electric propulsion on ships, diesel turbine propulsion on ships, and all sorts of other wonderful fun things. But that's for a channel that covers the latter part of the 20th century and beyond. Of course, you will probably be asking, now we've covered boilers and then the engines, well, the next logical thing to cover is the propellers that take the output of these two mechanisms and actually push the ship through the water. And you'd be perfectly correct. So, at some point in the next couple of months, we shall cover the development of the ship's propeller.
That's it for this video. Thanks for watching. If you have a comment or suggestion for a ship to review, let us know in the comments below. Don't forget to comment on the pinned post for dry dock questions.